So let's continue with our discussion of this Arzela-Ascoli theorem. Okay. So you know the situation is that we are trying to understand what compactness means for functions. Okay. Basically, we want to understand compactness for families of meromorphic functions defined on a domain in the complex plane. Okay. Or in the extended complex plane. Okay. But then we want to get some idea about what compactness means from basic topology. Okay. So as I was telling you, suppose you are having a topological space, you have the notion of compactness. Okay. And if the topological space is a metric space, then compactness is the same as it's equivalent to sequential compactness, and it's also equivalent to the Bolzano-Weierstrass stress property. The sequential compactness is the property that every sequence has a convergent subsequence. Okay. The Bolzano-Weierstrass stress property is the property that every infinite subset has a limit point. Okay. And these three are equivalent, right? And then there is also this implication that if you have a compact subset, it's always closed and bounded if you are in a metric space. Okay. But the converse is not true. So if you take R infinity, you can easily look at the unit ball in R infinity, the closed unit ball. It will be closed and bounded, but it will not be compact because you can write out a sequence which does not admit any convergent subsequence, namely the sequence consisting of 1 at the ith place and 0 elsewhere. Okay. Any two terms of this sequence differ by a distance of √2, okay, are separated by a distance of √2, and therefore this sequence cannot have a convergent subsequence. Okay, because the terms of the sequence don't come. You cannot find a subsequence whose terms, whose elements come closer and closer together. Okay, so but of course in any metric space, compactness implies closedness and boundedness. The converse is not true. The converse is true for Euclidean spaces, and in fact I even told you that if you take a Banach space, the condition that it is finite dimensional is equivalent. Every closed subspace, every closed bounded subspace is compact. If you want to put that condition, then the Banach space has to be finite dimensional. It cannot happen if it's an infinite dimensional Banach space. Okay, so now you see. All right, so so there is a related notion. There is this notion of total boundedness, okay, which is implied by compactness. All right, total boundedness is basically the property that you can cover the whole space by open balls of a fixed radius, no matter how small the radius is. But the point is, of course, by finitely many such open balls. Okay, so given any positive radius epsilon, I should be able to find just finitely many open balls of radius epsilon whose union is the whole space, and I should be able to do this for every epsilon greater than 0. This is total boundedness, is a very strong form of boundedness. This implies boundedness. Okay, and in fact a space that is totally bounded is actually it even has finite diameter. Okay, because the diameter of the space can be compared to the diameter of this finite collection of centers of these open disks, which is called a net, an epsilon net, if the radius you are talking about is epsilon. Okay, and the point is that total boundedness itself, though it is a strong form of boundedness, total boundedness is not enough to give compactness. Okay. What you have to add to it is completeness. So if you have something that's complete and totally bounded, a metric space that is complete and totally bounded, then it is compact. Okay, and so that is the so that's another equivalent version of compactness. So we check to check compactness, either you check the abstract definition of compactness, which is very hard. You have to take an arbitrary open cover and you have to show that there is a finite subcover. That's very difficult in practice. Okay, and probably if you are given a particular open cover, a specific open cover, maybe you might be able to, because of your knowledge of geometry and topology, you might be able to extract a finite subcover, but you can't do this in an arbitrary way. So it's abstract. Okay, trying to get hold of a finite subcover from any given open cover is a very abstract thing. It's not easy to check. Okay, so we end up checking sequential compactness. Okay, namely you take a sequence and show that there is a convergent subsequence. If you check that, then that's equivalent to compactness. The other thing you can check is that the space has the metric space has the Bolzano-Weierstrass property. Show that every infinite subset has a limit point. Okay, and of course, if you are if you are working with subsets of Euclidean space, you know what to do. You will just check that the subset is that you want to say is compact is both closed and bounded. So there is not much to do. All right, but point is that, and of course now there's also this extra condition that if you want to check a space is compact, you check that it is complete and it is totally bounded. Okay, and of course completeness is the condition that every Cauchy sequence converges. Okay, that is whether that can be easily checked or not depends on the particular case you are looking at. Okay, it's also not so easy. Okay, and the other thing is total boundedness, and that's also very abstract. Okay, total boundedness is a very abstract thing. You have to say that you can find an epsilon net for every epsilon greater than 0, and that's so you have to produce an epsilon net for every epsilon greater than 0, and epsilon net is those finitely many points in the space centered at which, if you take open balls of radius epsilon, these balls will cover the whole space. Okay, you have to show the existence of those finitely many points, that epsilon net, and you should do this for every epsilon. It's not an easy thing to do. All right, so these are the various versions of compactness that we have, but we are interested in compactness of functions. Okay, now for functions, what is it that is easy to verify? Normally what do you normally easily verify about functions? You verify continuity. Okay, you verify differentiability, you verify boundedness of a function. Okay, try to find a constant which bounds the modulus of the function values. Okay, so these are the things that you can verify. Okay, so you need something in the situation of functions. If you are working with a space of functions, then you need better conditions for compactness, and that's where the Arzela-Ascoli theorem steps in. So basically we are looking at a compact metric space X. Okay, so X is a compact metric space, and let me go back to what I wrote last lecture. X is a compact metric space, and let me use a different color now. X is a compact metric space, and you are looking at I am looking at this CXR, which is the it's the Banach algebra. It's a complete norm linear space of continuous functions on X with values in the real numbers. Okay, and you could have also taken with values in the complex numbers. You would get the other Banach algebra CXC. Okay, and the question is that you want to and of course, mind you, since X is compact and a continuous function on a compact set is uniformly continuous and always attains its bounds, every function that we are worried about is already uniformly continuous and it's bounded. Okay, so normally when you write CXR or CXC, you mean also not only just continuous functions but also continuous bounded functions. Okay, but here boundedness is automatic because X is compact. All right, so what I want to take a closed subset of I want to look at a subset of functions. I want to look at a family of functions or a collection of functions, okay, which you think of as a subset of this space of functions CXR or CXC, and I want to say that it is compact. That's my aim. I want to get a nice condition to say that a collection of functions is compact. Okay. Now since we are in a metric space, something that has to be compact, a subset has to be compact, means that it has to be both closed and bounded. So certainly this subset to begin with should be closed. Okay, so we put this precondition that it's already a closed set. If it's not a closed set, it's not going to be compact, because compact implies it's closed. Okay, and of course it has to be bounded, because I told you that in any metric space a compact subset is always closed and bounded. Okay, so if you start with a closed subset A, the condition that it is compact is equivalent to it being bounded, and here is the extra condition. The extra condition is equicontinuity. Okay, so equicontinuity is something that that helps us to get hold of compactness, right? So I want to see at this point, I want at this point say the following thing. I want to say that if you look at it from the viewpoint of total boundedness, okay, then you see to say that A is compact, it's enough to say that A is totally bounded. Okay, because if A is totally bounded, all right, then A is also complete. Not then, I mean A is already complete, because A is a closed subset of a complete metric space, so it's complete. And if you add total boundedness together with completeness, you will get compactness, because that's another characterization of compactness I told you. Okay, so if A is totally bounded, then I know it's compact. Okay, so the only issue is with replacing this total boundedness with something else, and I told you this total boundedness is not so easy to verify, because you have to show the existence of an epsilon net for every epsilon. It's not practical. Okay, so whereas total boundedness being difficult to verify, we have boundedness is easier to verify. Okay, so you from the total boundedness you remove the total and you just put boundedness, which is an easy thing to verify for functions. Okay, and because you have made the condition weaker from total boundedness to boundedness, you have to put something else to make it strong enough to get compactness, to give compactness, and that strong enough thing is the equicontinuity. Okay, so I will tell you what this equicontinuity is. Okay, so basically the idea is very simple. The idea is, see, if you want a function to be continuous at a point, then what you do is you say that there is the usual you have the usual definition of the epsilon delta definition of continuity at a point, and what is that? Give me an epsilon greater than 0, I can find a delta such that whenever the point is within a delta of the given particular point, then the function value is within an epsilon of the image of the function value at that point. Okay, now so the whole issue here is that if you change the point, okay, so you are looking at continuity at a point for a given epsilon, you have to verify it. Okay, now the delta that you get will depend on the epsilon, of course, because if you make epsilon smaller, you might expect that the delta must become smaller. Okay, and so the delta depends on the epsilon, the delta also depends on the point, and the delta is particular to that function. Okay, so the delta depends on three things. Okay, delta depends on three things. If you are so let me write this down. So what is this equicontinuity? So you see, what is the usual continuity? Usual continuity at, let us say, x naught for f. What is this? Given epsilon greater than 0, there exists a delta greater than 0 such that whenever the distance between x and x naught is less than delta, then we have that the distance between fx and fx naught is less than epsilon. This is the usual good old definition of continuity, epsilon delta definition of continuity. And you see the point here is that of course this the first d that I use in d of x comma x naught is the metric on the space on which the function is defined, whose points are x and x naught is a fixed point, x is a variable point. Okay, so basically this dx comma x naught less than delta refers to, basically it refers to all the points in a delta open ball centered at x naught in your space. Okay, and what you are saying is that whenever you take a point in a delta open ball centered at x naught, then its image is in an epsilon open ball centered at fx naught. That is what you are saying. Okay, so the image of this delta open ball under f goes into this epsilon open ball centered at fx naught. Okay, that is what usual continuity is. But the point is that this epsilon, you see, the given an epsilon, okay, delta depends on what? See, it depends on of course epsilon, it depends on x naught, and it depends on f also. Of course we are looking at a single function, so we forget the function, because if you are dealing with only one function there is no confusion. But if you are looking at a family of functions, then you will have different functions f. Okay, and as you change the function for the same epsilon and even for the same point, okay, if you have family of functions which are continuous at a point x naught, okay, then for that family of functions, even if you take a single epsilon, the same delta will not work, the delta will change with the function. Okay, and of course the delta will change with the point. Now equicontinuity is the fact that is the condition that you are able to get a delta that works for all functions in one stroke. That is equicontinuity. Okay, so a collection of functions well, A, so let me call it as A, is called equicontinuous at x naught, if given epsilon greater than 0, we can get a delta that works for all functions in that collection. That is equicontinuity. You get a common delta, that is equicontinuity, alright. And well, and of course if you say that a family is equicontinuous on a subset of the space, if it is equicontinuous at every point of the space. Okay, so you make a pointwise definition and then you say that this definition holds if it holds for a subset of points, if it holds for every point in that subset. Okay, so this is just like saying that a function is continuous on a set if it is continuous at every point of the set. It is like that. So A is equicontinuous at or let me say on let me say subset y in x if it is or let me use x prime if it is equicontinuous at each point of x prime. Okay, so this equicontinuity is basically, if you want to think about it in a very simple way, equicontinuity is given an epsilon, you find a delta that works for all functions. That is the point. Okay, a single delta will work for your epsilon for every function in your collection. Then that collection is called equicontinuous, an equicontinuous collection or equicontinuous family of functions. Okay, and what the Arzela-Ascoli theorem says is that, well, the Arzela-Ascoli theorem says that if you put equicontinuity together with boundedness, then that is good enough to say that your collection is compact. Okay. So, compactness of a family of functions is equivalent to that family being equicontinuous and bounded, and mind you, this is a much nicer condition than total boundedness. Okay. Equicontinuity is it's a kind of continuity that you have to check. It's just continuity you have to check, but make sure that you get one delta for all the functions for a given epsilon. Okay, that's like checking continuity, and that should be far more easier. Checking boundedness is not should not be a big problem. Okay, so these are all things that we normally check for functions, but given a family of functions, you never it's not common that you check total boundedness. Total boundedness is you have to find finitely, given an epsilon, you have to find finitely many functions, so that the distance of any function is within an epsilon to one of these finitely many functions. You have to find this epsilon net. That is not easy, and that is not common. Okay, it is not practical. So Arzela-Ascoli theorem helps you by saying that, well, you want to check a family of functions is compact, do not do much, you just check that it is bounded, check it is equicontinuous, and you are done. Okay. So I just wanted to indicate something about the this equivalence of compactness with boundedness and equicontinuity, because it's a very fundamental thing, and you need to know how things work. Okay. So let me do the following thing. I'll again change color and use a different color. So I'll say proof of Arzela-Ascoli. So let me go through the proof, because I want you to understand the ideas involved. Okay, you will also get familiar with all these notions of total boundedness, epsilon net, and how equicontinuity is actually used. Okay, so start with a closed A inside CXR. Okay, start with the closed set. What do you have to show? You have to show that A is compact if and only if it is bounded and equicontinuous. Okay, so assume A is compact. Assume A is compact. All right. Now, what do you have to show? So this is one way of the theorem. You have to show that if it is compact, it is bounded and it is equicontinuous. Okay. I told you that in a metric space, a subset is compact implies it's both closed and bounded. Okay, so it's bounded. Okay, compactness always implies closeness and boundedness in a metric space. Right. So and mind you, that's true only for metric spaces. If you go to arbitrary topological spaces, things can become very bad. You can have a compact subspace of a compact topological space which is not closed. Okay, it can behave terribly. You can have a whole space which is compact. You can have a subspace which is compact, but the subspace is not closed in the whole space. This can happen for an arbitrary topological space. It cannot happen for a metric space. For a metric space, compactness always forces closeness and boundedness. So, Hausdorff spaces also. Hausdorff spaces if you want. Yeah. So you see, so assume A is compact, then A is bounded. Okay, because compactness will imply closeness and boundedness. It's all A is already closed. Okay, but we want boundedness. That is implied by compactness. We only have to show that A is equicontinuous. Okay, we only need to show A is equicontinuous. Okay, that's what you have to show. So you see, so incidentally, let me make a remark here. In this case, we are anyway going to the way we prove the Arzela-Ascoli theorem is by using the other version, characterization of compactness, which is compactness is equivalent to A being totally bounded. Okay, this total boundedness will come into the picture, okay, at least in the proof. Okay, that's the key tool that helps in the proof of the Arzela-Ascoli theorem. So if you think of if you think of that, given that A is compact, I know it's totally bounded, and I told you totally bounded also is a strong form of boundedness, so it implies boundedness. Totally bounded is the condition that there is an epsilon net for every epsilon, okay, and you know that the diameter of the space can be compared to the diameter of any epsilon net, okay, to within an epsilon, okay, or 2 epsilon, okay. So therefore A is always bounded, in fact it has finite diameter, alright. You only need to show that A is equicontinuous, and for the equicontinuity also you use the fact that it is totally bounded, okay. So since A is totally bounded, well, A is A admits an epsilon net for every epsilon greater than 0, okay. So here I am using the fact that compactness implies total boundedness, right, and compactness implies total boundedness is a very it's a very simple thing, there is nothing complicated about it, okay. Basically what you are saying is that you should cover the space by finitely many open balls of a fixed radius, okay, that radius being epsilon, and that's very easy to see, because if you take all open balls of radius epsilon, that's a cover for the space. You allow every point of the space to be a center, and you take the collection of all open balls of radius epsilon, that's obviously an open cover for the space, and if you know it's compact, it has to admit a finite cover, and that finite cover, if you take the centers, that will give you the epsilon net that you want, okay. So it's that compactness implies total boundedness is absolutely easy to see, okay. So there is an epsilon net, okay. So so let epsilon greater than 0 be given, and let us take so here is a this is the kind of thing you fiddle with to get epsilon finally in your answer. So usually the idea is that you use a triangle inequality, finally all these epsilon arguments, they finally end up with a triangle inequality. If you are breaking a distance into 2 pieces, then you try to, and you want that distance to be less than epsilon, you try to make each piece less than epsilon by 2. If you are breaking it into 3 pieces, then you make each piece less than epsilon by 3. So what I am going to do is, I am not going to take an epsilon net, I am going to take an epsilon by 3 net, okay. So so let epsilon greater than 0 be given, and let us take an epsilon by 3 net for A, okay. So what does this mean? This means that there exist functions f1 etc. up to fm which are in A, such that, well, the any function in A such that for any function in A there exists an I such that I with the distance between f I and f less than epsilon by 3, okay. So this is what epsilon net means. Basically you cover all points of the space by looking at open balls of radius epsilon by 3 centered at the points which correspond to the epsilon by 3 net, right. This is what you get. Now I want you to at this point I want you to remember what is this distance here. See, this distance is the distance in the Banach algebra CXR, okay. It's, mind you, all these what is A? A is a subset of CXR, and CXR are functions which are continuous functions on x, real valued functions, okay. And so what is the and of course x is compact, so these all these functions are bounded, okay. Continuous function on a compact set is bounded, and in fact it is uniformly continuous and it attains its bounds, right. So so what is the distance? The distance is the supremum now. So what is this? This quantity is supremum as x belongs to capital X, as x varies over capital X, of mod of fi of x minus f of x. This is what it is, okay. In fact it is precisely norm of fi minus f. That is what the distance is. The distance between fi and f is just norm of fi minus f, and the norm is a sup norm. So you calculate fi minus f at each point, and then you take the mod of that, and then you take the supremum, okay. And this should be less than epsilon by 3. This is what you have, okay. This is what you have. Now you see, now we are kind of in more or less in a very good good shape, because see now you can get equicontinuity very easily. So let us check equicontinuity at a point, okay. So let us check equicontinuity at x naught in x. Let us check equicontinuity there, okay. Then what is it that is going to happen? Well, what do you have to check for equicontinuity? You have to find a delta such that whenever mod x minus, whenever the distance between x minus x and x naught is less than delta, okay, the distance between fx and fx naught is less than epsilon, and this should work for all f in your family A, in your collection A, okay. So given for the given epsilon greater than 0, we seek delta greater than 0 such that mod, I keep saying mod because at the back of one's mind one keeps thinking of Euclidean space, but it is not mod, you should replace it with d. So the distance between x and x naught less than delta implies that mod fx, the distance between fx and fx naught, which is mod fx minus fx naught, is less than epsilon, and this should work for all f in A. This is what you want, alright. So so you see, how do you do this? The idea is very simple. There is this, on the one hand you have an x which is a variable point, you have this point x naught, okay, and you have an arbitrary f, alright, and you will have to now connect that arbitrary f in A with these particular fi's which are the elements of the epsilon net, okay. So you do that by basically by using a triangle inequality to break down some distance into 3 pieces, okay. So what you do is that, well, you write this mod fx minus fx naught, you write this as, I have already told you that given this f, there is an fi with the property that the norm of fi minus f is less than epsilon by 3, that is already there. So use that fi. So you write this as modulus of f of x minus fi of x plus mod fi of x minus fi of x naught plus modulus of, so I should put less than or equal to modulus of fi of x naught minus fi f of x naught. This is what I will have to do, okay. So I introduced this these fi cleverly, fi values at x and fi values at x naught to break this, and then what happens is that you see f for any x in x, okay, for any x in x, the modulus of Fix minus Fx is always less than epsilon by 3. So the point is that this fellow here, this is less than or equal, this is less than epsilon by 3, okay, and so is this fellow here, this is also less than epsilon by 3, okay. I have to be worried only about the central term. This is the only term I have to worry about. That's I can't apply that epsilon by 3 bound to that because the points are different. The function is the same, it's the same Fi, okay, it's the same Fi, but the points are x and x naught. Whereas in the first term the point is x, the third term the point is x naught. The term in the middle has 2 points with the same function, okay. What do I do that? What do I do here? So here what I do is basically I use the fact that all these Fi's are all uniformly continuous. In fact, they are all continuous. They are continuous on a compact set, so they are uniformly continuous. So because they are uniformly continuous, I can make sure that, you know, if I choose a delta sufficiently small, whenever the distance between x and x naught is less than delta, I can make the central term less than epsilon by 3. I can do this. In fact, I can simply do it because of continuity of Fi at x naught, but the point is that I can do this for all Fi at the same time because there are only finitely many Fi's, okay. There are only finitely many Fi's. See, for if I want Fix minus Fix naught to be less than epsilon by 3, I can of course choose a delta such, I can find a delta for which whenever the distance between x and x naught is less than delta, then mod Fix minus Fix naught is less than epsilon by 3. I can do this because of continuity of Fi at x naught, okay. But then this delta may depend on the Fi, okay, and if I change the I to other Fi's, okay, then the delta will change, but there are only finitely many of these Fi's, so I could have taken the minimum of them and that would work for all Fi's, all the elements of the epsilon net in one go, alright. And mind you, you could even forget the point x naught. That's because all these functions that we are studying, they are all uniformly continuous, okay. So there is also you can not only do this you can not only do this for all the Fi's because they are finitely many, you can also do it irrespective of the point x naught because of uniform continuity. That is because all the Fi's, all the functions we are considering are continuous functions on a compact space, and when you have continuous functions on a compact space, you get uniform continuity. Uniform continuity is that whenever the distance between source points is less than a delta, then the distance between the image points is less than epsilon. It does not matter what the source points are, the only condition is they have to be within a delta. You can find such a delta, that is that is uniform continuity, okay. So so let me write here can find a delta greater than 0 such that mod Fi of x minus, so let me write Fj of x minus Fj of x naught is less than epsilon by 3 if d of x comma x naught is less than delta because and for all j. So let me write for all j because of continuity of Fj at x naught and the fact that there are only finitely many Fj, okay. I can do this, right. Not only that, I can do more. In fact, because all of these are uniformly continuous, I can do this irrespective of x naught, okay. I can even forget the x naught, okay. In fact, since the x is compact and Fj are uniformly continuous, so I am abbreviating it to UFLY for uniformly continuous. we can do this for any x naught. Okay. So you can find, given an epsilon, you can find a delta which neither depends on the f nor does it depend on the x naught. Okay. So you have verified equicontinuity in a uniform way. Okay. And that's how, so you've got equicontinuity, that's it, you have found a delta that works for every f. Okay. So thus A is equicontinuous. Okay. So the moral of the story is we are able to see one way why, if you have a compact space of functions, then these functions must form an equicontinuous family. Okay. So equicontinuity is something that is very important, and mind you, I will have to prove the other way of the theorem, but then before I do that, which I will do in the next lecture, what I will now say is, I will tell you why this is called, why Arzela-Ascoli's theorem is sometimes called the uniform boundedness principle. It is because of the following reason. You see, the condition is that a closed subset of functions is compact if and only if it is bounded and equicontinuous. Okay. Now this bounded is actually bounded with respect to the metric on the space of functions, and that's given by the sup norm. Okay. And boundedness under the sup norm, okay, is actually uniform boundedness. It means, see, what does boundedness normally mean? It means that you are able to find a positive constant such that the modulus of the function values at all points is bounded above by this positive constant. Okay. But of course this positive constant would change if you change the function. So if you take different functions in a family, each function may individually be bounded, but you may not be able to find a common bound for all the functions in the family. Okay. And that is what uniform boundedness does. It gives you a common bound for all functions in your family or collection or subset. Okay. So boundedness in CXR actually means uniform boundedness, and Arzela-Ascoli's theorem is just that if you have a uniformly bounded family which is equicontinuous, then it is compact, and conversely. That is what Arzela-Ascoli's theorem is. Okay. And that is why it is called the uniform boundedness principle. Okay. So I will continue in the next lecture and try to tell you the other way of the proof. Okay.